Hello, in this video we'll be talking about quantum numbers, and I'll show you how to find quantum numbers and how to write out the quantum numbers for specific elements. So a set of quantum numbers is basically the address for an electron. So in quantum mechanics we really want to get down to specifics on electrons. In particular, we want to know the most about the electron that we can. And so in order to do that, we've got a series of progressively specific numbers called quantum numbers. And there are 4 quantum numbers. And they're represented in a set like this, where they're separated by parentheses. So the first quantum number is called the principal quantum number. And it's signified by this letter N, and it represents the energy level of your electron. So remember that our energy levels can be positive integers. N equals 1, N equals 2, N equals 3, so on. You learned that with the Bohr model. Same thing is true for quantum mechanics. And your N is also going to correspond to the row of the periodic table that your element is on. So let's say, for example, your element is on row 2. That means you've got N equals 2. So the row number is the same as the principal quantum number, the energy level. So energy level is the same as the row number. Row is 2, energy level is 2. They correspond together. The second quantum number is called the angular quantum number. And it designates the subshell that your electron is in. And that's going to be symbolized by the letter L, a cursive L. And your L values correspond to those letter designations that we learned about before. So when L is equal to 0, that means you're in the S subshell. When L is equal to 1, you're in the P subshell. When L is equal to 2, you're in the D subshell. And when L equals 3, you are in the F subshell. And that's going to be the second quantum number right here. So if you look at your set of quantum numbers and you look at the second one, that's going to be the one that tells you if you're in the S block, the P block, the D block, or the F block. And it's all based on what that L is equal to. The third quantum number is called the magnetic quantum number. And it's symbolized by this M sub L. So M and then a little l. And that's going to be the orbital that you're in, that your electron is in. So each subshell, each L value is going to have specific orbitals associated with it, and the orbitals where the electrons actually end up going. That's where the electrons are in the orbitals which we designate as M sub L. And this fourth quantum number here is going to be called the spin quantum number. And we learned before that electrons in the quantum mechanical model are associated with spin, upspin and downspin. And we're going to show that in the quantum numbers with plus and minus 1/2. So upspin is positive 1/2 and downspin is negative 1/2. And just as a rule of thumb, we have this principle here called the Pauli exclusion principle. And the Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. So no 2 electrons share the same 4 quantum numbers. Each electron is going to have its own unique set of quantum numbers. It's not going to share those with any other electron. So let's do a little practice down here really quick before we actually jump into an element. So remember that all of these quantum numbers are basically going to relate to one another. And so remember that N, which is the energy level, corresponds to the row of the periodic table. And that's going to be your energy level. So that's the energy level at which your electron is at. And the L goes from 0 up to n minus 1. So let's say hypothetically you have n equals 4. So when your n is equal to 4, your L values are going to equal 0, 1, 2, and 3. Because we go from 0 up to n minus 1, which 4 minus 1 is equal to 3. So when your n is equal to 4, you go up to 3. And you need to write each of these out because each one of these is an individual subshell that could be in your element. And there's going to be specific m sub l's that go along with this. So m sub l is designated by going from negative L up to 0 and then up to positive L. So I'm going to make this row right here our possible L values. So in this case, we wrote them out here. So we can have 0 for our L, we can have 1, we can have 2, and we can have 3. And remember, this is just the L values that I've just written. So when your L is equal to 0, your m sub L is going to be equal to 0. That's the only option for L is equal to 0. When your L is equal to 1, we're going to go from negative 1 to 0 to positive 1. Because for the m sub L, we go negative L up to 0 up to L. So for L equals 1, we go negative 1 up to 0 up to 1. When L is equal to 2, the m sub L's are going to go negative 2, negative 1, 0, 1, and 2. Going from negative L up to 0 up to positive L. And for L equals 3, you start at negative 3, negative 2, negative 1, 0, 1, 2, and 3. So hopefully you kind of see the pattern now where you are just going from the negative L value up to 0 and then up to the positive L value. And you would need to list each of these out. And we're actually going to look at that in just a second when we look at an example of an element. And what I always do, and what I recommend you do as well, is when you're writing out your quantum numbers, write them based on energy level and based on L value. So what I would do is I would split up each individual energy level and do the quantum numbers for that energy level. Because most of your elements are ultimately going to have multiple energy levels associated with them. And we're going to look at that in just a second. So I recommend you split that up and you kind of just take it one L value at a time. Worry about the electrons in one subshell, then move to the next subshell and the next subshell, and eventually you'll get them all down. So now let's go ahead and look at an example of that in practice. Okay, so here's our practice problem here. So we want to list all of the quantum numbers for oxygen. So remember, oxygen is here. It's element number 8, which means it's going to have 8 electrons. Its atomic number is 8 electrons. So we're going to have 8 total electrons to account for in our quantum numbers. Because remember, each set of quantum numbers is linked to 1 electron. So if we have 8 electrons for oxygen, that means we're going to have 8 total sets of quantum numbers. So take note of where oxygen is on the periodic table. It's in n equals 2. So because it's in n equals 2, it's going to be n equals 1 is going to be its first energy level, and then n equals 2 is going to be its second energy level. Because these energy levels stack on top of each other. So if your element is in the second row, it's going to have n equals 1 and it's going to have n equals 2. It's not just going to have n equals 2. It's going to have both of them because they stack onto each other. So like I said, what I'm going to do is I'm going to split these up based on energy level. So I'm going to tackle the quantum numbers for n equals 1 first. So we know that when n equals 1, this first quantum number is going to be 1. Because 1 is just n. Well, the first quantum number, I should say, is just n. So that's going to go right there. Our second quantum number is going to be our L value. And in this case, when n is equal to 1, the only thing L can be is 0. And then for our third quantum number, it's going to be negative L up to 0 up to L. Well, in this case, our L is just 0, so our M sub L is also just 0. And then we want to start with the positive 1/2 first. So you're always going to want to fill up the positive upspun electrons first for each L, and then once you fill up the positives, then you want to go back and do the negatives. And that's a principle known as Hund's principle, and we'll talk about that a little more with electron configuration. But if you took chemistry in high school, you probably learned it as the empty seat rule, or like the bus seat rule, where you fill up the upspun first, and then you go back and do the downspun. And that's what we're doing here. So for the second one, we're going to have n equals 1, L equals 0, M sub L equals 0, and then we're going to put that negative 1/2 in. And that is it for n equals 1. So for n equals 1, we've covered both electrons for that. Now we're going to move on to n equals 2. So remember, for n equals 2, our L can be 0 and L can be 1, because we go from 0 up to n minus 1, which in this case is 1. So we're going to cover both L equals 0, and we're going to do L equals 1 for the second energy level. So for our first quantum number, I'm going to put 2, because that's what our n is now. Our n is equal to 2, so that's our first quantum number. And we're going to start with L equals 0. So I'm going to put 0 right here. And then just like before, we're going to have this whole thing here, just like before, where we have 2, 0, 0, and negative 1/2. Because like I said, you want to take it each L one at a time. So now we can worry about when L equals 1. So we've done L equals 0, now we want to do L equals 1. So we're going to start with 2, 1, negative 1, because remember, when L is equal to 1, our M sub L can be negative 1, 0, and 1. So we're going to start with negative 1. And we're going to use Hund's rule to put the positive upspun electrons first. So plus 1/2. Then we're going to do the next one here. And now we're going to do 0, because we're going negative 1, 0, again with the positive 1/2. And then we're going to do 2, 1, positive 1, positive 1/2. So now, because like I said, you kind of want to separate each L value. So separate each L value when you want to apply Hund's rule. So we've put all of the upspun electrons for L equals 1, right here, these 3. Now we can go back and put the negative, the downspun electrons. So we'll do 2, 1, going back to negative 1, so we're circling back, negative 1/2. So we filled up all of the positive 1/2s. Now we can go through and do the negative 1/2s. However, for oxygen, this is going to be our last electron, because oxygen has a total of 8 electrons, and if we count our sets here, we have 1, 2, 3, 4, 5, 6, 7, 8. That's all of our electrons. So once you have done all of the electrons for your element, that's when you stop with the quantum numbers. So your quantum numbers stop with the element's total number of electrons. So we've got 2 here, 2 here, and 4 here. And remember how we said that the L value is going to tell us what subshell we're in. So right here, we're in the 1s subshell, because n equals 1, that's where the 1 comes from, and s is because we have L equal to 0 here. These 2 electrons are going to be in the 2s subshell. 2, because we're now in the second energy level, n equals 2, so we put the 2 in front, and s, because these 2 have L equals 0. And these 4 electrons here are going to be in the 2p subshell. 2 because our energy level is 2, and p because our L is equal to 1. So that's going to sort of be a nice segue into doing electron configuration, which is a far simpler way to do this. So that's basically it for quantum numbers. That's about as complex as they'll get. Again, just some helpful tips. I would split everything based on your n value, so n is equal to 1, n is equal to 2. I would split those up, and I would also do it 1L at a time. So do your L is equal to 0 first, then do your L is equal to 1, then do your L is equal to 2, however many you need for the total number of electrons you have. So hopefully that allowed all of that to make a little more sense, and in the next video we'll be covering electron configuration and orbital diagrams.